All right, welcome everyone. Today we're going to be talking about parametrizing curves, mainly curves of intersection between two surfaces and also arc length. And this is our pre-class video. We're kind of leading up into those topics, but I found that there are a few like web work homework problems that don't exactly kind of fit into these, parametrizing curves of intersection between two surfaces and arc length. And so I thought it'd be a good idea to spend our pre-class video time talking about these other topics. Mainly, we are going to want to parameterize tangent lines for vector functions. We're going to figure out where a curve and a surface intersect. So rather than two surfaces, right, a curve and a surface. And then we'll also be able to talk about where two curves intersect as well. So without further ado, let's get to it. We saw kind of last time, right, that we can obtain a tangent vector. That's one of the things that the derivative is used for, right? And so with that, we can actually figure out a nice, tangent line equation as well. And so that's what we'd like to tackle with here. So here we have a quite complicated curve, right? And I would like to find the tangent line equation for this. Now, remember, we learned back in 12.5 that anytime that you want a line, right? Tangent line is just a special type of line. You really need two things. You need a direction vector and you need a point that that line goes through. And so luckily, right, because we have a specified time, we can plug that in, that special time, t equals 1, into this, right? And let's see, 1 squared is going to be 1, square root of 1 is going to be 1, and then we're going to have 1 times e to the 0. And we can verify in our calculator or whatnot, or maybe just remember the rules of exponents, but anything to the 0th power is 1. So this is really 1 times 1. And so, well, that's just going to be equal to 1. So we have the special point, right? At t equals 1, right? The point is 1, 1, 1. The other thing that we need is a direction vector. But again, right, we saw last time that we can get this thanks to the derivative. And so I want to find the derivative of this vector function here, and then I'm going to plug in my special time, and that will give me the good direction vector, right? So, okay, let's go ahead and take the derivative of this. This will take probably a minute. Well, this one's not so bad, right? The derivative of t squared is 2t. The derivative of the square root, well, remember the square root is the same thing as raised to the 1/2 power, right? So this is equal to t to the 1/2 power. So if I take the derivative of that, the 1/2 comes down and I reduce my power by 1. And then finally, the derivative of t times e to the t minus 1. Well, that's a product of two functions. So we're going to need to use the product rule. So the derivative of the first times the second plus the first times the derivative of the second. And while the derivative of e is itself, but then you also have a small chain rule here. And inside there you have t minus 1. But luckily the derivative of that is just 1. So there we go. And so now we can go ahead and plug in our special time to figure out, right, the direction vector at t equals 1. So with that, what we're going to have 2 times 1 is 2. 1 raised to any power is very nice. It's just 1. So this is 1/2. And of course, you can verify with your calculator that's 1 raised to the negative 1/2 power is indeed 1. So it's just 1/2 times 1. And then let's see here. We're going to have 1 e to the 0 plus 1 e to the 0, right? And again, e to the 0 is just 1. So really, this is just 1 plus 1. So this is going to be 2. So this right here will be our good direction vector for our tangent line. And so overall, the equation of the tangent line can be given by, and quite often, right, so we already have this thing r of t. It's some complicated curve. And so I don't want to reuse r here. So because it's a line, maybe let's use L. So the tangent line is given by, and again, for any line, we need a direction vector and we need a point that we're going through, right? So in this case, our direction vector is going to be given by our derivative. That's the bit that goes next to the t. And then the point that we're going through, right? Well, that's 1, 1, 1. That's the constant there. And of course, if you'd like to, you can go ahead and combine this nicely into just one vector equation here. So that would be what? 2t plus 1 in our first coordinate, and 1/2 t plus 1 for our second, and then 2t plus 1 for our third. And again, in order to get the entire line, you would allow t to range from -infinity to infinity. Or another way that you could put that is that t is in all real numbers. So you could just use one of these script r's here if you'd prefer. So that right there will be our final answer. And so with this, I think it's a good idea to maybe write down a formula or kind of try to bottle what we came up with here, right? And so here we have a theorem, the equation of a tangent line to some parametrized curve r of t. And this will work for really any complicated formula here. At some specified time, right? So t equals 1 in our case, but you could have 2 or 5 or whatever. So we're going to try to leave it as generic as possible. We're going to do t equals a here, is going to be given by, and again, you're going to need to have a direction vector, and that's going to be given by the derivative at that special time. And this is what you're going to multiply by your t. And then you need to add on, right, the point that you go through, right? In this case, it's r at a. So you can see that this actually isn't even so far off from our good old equation of a tangent line back from our Calculus 1 days. And so this is actually quite nice. All right. So that's kind of the first set of problems that you may see in your web work homework, and consequently, right, you can see these on quizzes and exams. Another thing that I'd like to be able to do, and again, this is kind of an upgrade from 12.5, is we're going to end up working towards the intersection between two surfaces, right? Right now, we're going to just deal with a curve and a surface, but eventually we're going to get the intersection between two surfaces. And right, just like we did in 12.5, we found that a line was the intersection of two planes, right? And so if you have two surfaces, right, you're going to get some generic curve, maybe, the intersection between two surfaces. So let's go ahead though and work on this one here. So we have a curve, which, by the way, if you'd like to, you can write this in the angled bracket notation, right? And you can clearly see, right, there is no I components. So there's 0 for I, t for j, and then 4 minus 3t for your k component. So if this helps you, right, I would recommend that, switching to this angled bracket notation. And we want to know, where does this intersect the surface? And the big thing, right, is that when you have a vector curve like this, right, you have an x component, a y component, and a z component, right? So this is the vector form, but you can also write this as a set of parametric equations. And in that case, you would do x equals 0, y equals t, and z equals 4 minus 3t. So this is how you would express the same curve, but rather than in the vector formula, right, a set of parametric equations. And I find that this is the most useful, right, because it kind of gives you this good idea. We're trying to figure out where two things intersect. And quite often in algebra days, right, if you wanted to know where two things intersect, right, you would set them equal to one another, right? Or you would substitute in, right? There was that action, that algebraic action that goes with the kind of the geometric idea of where do these things intersect. Because you got basically some interesting surface here. I don't know what it looks like, maybe something like that. And you have some interesting curve, right? And somewhere, maybe they intersect. And they could actually intersect in multiple places, right? Maybe it comes back through and it intersects a second time. But that action of, right, intersecting quite often algebraically comes down to, right, substituting in, right? And so in particular here, when you write this as x equals 0, y equals t, and z equals 4 minus 3t, I think it's very natural to say, okay, let's substitute those into the surface equation. And that should help us figure out when the curve intersects the surface. And by the way, we did the same sort of trick back in 12.5, right, when we asked where does a line intersect a plane. So this is not technically new. We've done this before. We just substitute in these equations into the surface. Previously, it was a plane. So let's do that, right? So 4 minus 3t is equal to 0 plus t squared. So that is everywhere I saw an x, I substituted in x. Everywhere that I saw a y, right, I substituted in t. I think I said x for the other one. I substituted in 0. So here, t. So instead of, right, y squared, I wrote t squared. And then finally, everywhere that I saw a z, I substituted in 4 minus 3t, right? And so that's how I came up with this equation here. So now let's go ahead and solve, and this will give us at least the time values, right, where we have some intersection. And so I see that this is looking awfully quadratic-y. And so I may go ahead and try to rearrange this, right? When I used to solve quadratics back in our algebra days, I found that it was very nice to get everything on one side. So I'm going to write this as t squared plus 3t minus 4, and that'll give us just 0 on the other side. And now with this, right, with our quadratics, I really hope these things factor, but remember, you do have multiple ways of solving quadratics. So you could complete the square if you really wanted to. You could use the quadratic formula if you wanted to, right? There are multiple ways. But after staring at this for a little while, I hope that we all agree that this thing actually factors, right? That you can make this t plus 4 and t minus 1. And so that means that there are actually two intersection times. And those times would be at t equals -4 and t equals +1. So notice if this asked, right, at what t values, or even it may say when does the curve intersect the surface, right, we'd be done at that point. But instead it asks, right, at what points does it intersect? And so since we have these good time values, remember with this curve equation, it will input t values and it will output an x, y, z triplet, right? And so we're going to go ahead and feed these, the t equals 1 into our curve, and we're going to get 0, 1, 1. And then the other thing, right, is when t equals -4. So if I plug those in, right, I would get 0, -4, and let's see, -3 times -4 would be 12. Plus 4 is going to be 16, I believe, altogether. So there's actually 2 points where they intersect. Those points are going to be at this 0, 1, 1, and this 0, -4, +16. And of course, if you were paranoid and you wanted to double check your work, by all means, you certainly can, right? You would plug those into our surface equation up here and see that those work. So for instance, if you plug in 0 for x, 1 for y, and 1 for z, you'll see that that equation is satisfied. And likewise, if you plug in 0 for x, -4 for y, and 16 for z, again, you will see that that satisfies our surface equation. And so those are the 2 points that are both on the curve and on the surface. All right, well, so that's how we can deal with, right, a curve and a surface, right? Basically, it's just setting it up, plugging in those curve equations into your surface equations, and then solving for t. And then if you need to, right, you can go ahead and plug those back in to our curve equation to get a set of points, right? An x, y, z triplet. All right. Well, a bit more difficult, though, is that we could ask, what about two curves, right? So I have two curves here, and it's customary, right, that you use different variables, right? So that way you can kind of distinguish here. But I want to know when these two curves intersect. So notice variables, of course, is kind of what we usually use, instead of the word parameters. So we have the parameter t here, the variable t, and the parameter s, or the variable s for this one. But they're two separate curves. And the question is, at what point do these two curves intersect? And right, remember, two curves are, and really anytime you have stuff intersecting, right, you would like the x, the y, and the z, all to be the same. So mainly, I would like my x coordinate here to be the same as the x coordinate here. So t should be equal to 3 minus s. Then the x coordinates would be equal to one another. I also want my y's to be equal, right? So that is 1 minus t should be equal to s minus 2. And then finally, if these two curves are intersecting, right, we would like the z's to be equal. So that is 3 plus t squared is equal to s squared. And so if these two curves intersect, we really would like all three things to be true. And so again, kind of, this is very similar to, again, back in our algebra days, if you want things to be intersecting, right, quite often you take the equations, right, and you set them equal to one another. And so in this case, because there's kind of three sets of equations, x's, y's, and z's, unfortunately, you have to do all of them. Okay, so basically what we have here is a system of equations. Now, for a system of equations, right, there's just two variables here, s's and t's. And so really, we only need two of these equations in order to solve for the two variables. And so I'm going to hone in on, and I'm kind of more comfortable with these first two equations here, just because they're linear, right? These ones have quadratic terms, t squared and s squared. And so it's very possible that, maybe that's not too complicated. But usually what I do if I get a set of equations like this is that I usually try to identify the two easiest ones. So I think those first two are the two easiest ones. And again, anytime you're trying to solve for two variables, right, you really only need two equations. So I'm just going to choose those two. And then we have to solve a system of equations, right? Just like we did back in our algebra days. And so there are lots and lots of ways that you can solve a system of equations like this. And really you have to choose, I guess, basically your favorite, right? What is your favorite way to solve this system of equations? So that's going to be stuff like substitution or linear combinations, or if you're really like matrices, I suppose you could use like Kramer's rule, stuff like this. In this case, because I have it set up t equals, it'd be very easy to take this and substitute it in. All right, and let's see what happens here. So 1 minus, and instead of t, I'm going to write 3 minus s is equal to s minus 2. So let's see, we're going to have -2 minus a negative s, so that's going to be plus s, is equal to s minus 2. And so we can simplify this down, and it just gives us 0 equals 0. Now, this won't always necessarily happen, but you can see that this didn't actually help us solve our system of equations. And so sadly, I'm going to need to try something else. And this does occasionally happen. And that's why I wanted to bring it up in this example, just to show you that sometimes you may get something that doesn't really help you solve for what t is equal to and what s is equal to. And so in that case, okay, we will reluctantly kind of bring in the third equation. So I'm going to go ahead and focus in on the first and the third equation. Even though it's a bit more complicated, it turns out that we need it because the first two really didn't help us solve for what t and s need to be. So I'm going to do the same idea, right? We have t equals in the first case, and I'm going to go ahead and substitute that into my third equation instead. Everywhere I see a t, I'm going to put 3 minus s. So let's go ahead and do that. So this is going to be, let me do it over here. So 3 plus, and instead of t, I'm going to do 3 minus s, quantity squared, is equal to s squared. All right, let's spend some time simplifying that. So we're going to expand out the 3 minus s quantity squared. So we need to do the first, the inners, the outers, the lasts, all that sort of stuff. You need to really FOIL this out. And when you do that, right, you should get this 9 minus 6s plus s squared. And now very nicely, we can subtract away s squared from both sides and spend a little bit of time rearranging, right? And we can get that 12 is equal to 6s. So that means that s is going to be equal to 2. So this actually helped us solve for s explicitly. With that, we can now plug it back into really any of these equations, and all of them will tell us that t is going to be equal to 1. All right, that's the only one that kind of has them all in common here. And with this, right, so we found the good times. So when s equals 2 and t equals 1, supposedly these curves intersect. But we do have to be careful because we do have these 3 equations and yet only 2 unknowns. We do have to verify that all 3 of these equations are satisfied at these 2 values. So at t equals 1, t equals 1 and s equals 2. Let's go ahead and plug those into our 2 original equations. So looking at this one first, right, we have R1 at time 1 is going to be 1, 0, and 4. Now our second curve, right, depends on s. So we're going to have s is 2 in this case. And when I plug that in, we're going to have 1, 2 minus 2 is going to be 0, and then 2 squared is going to be 4. So again, we were plugging in everywhere we saw an s, a 2. And indeed, we see that these 2 curves actually do intersect at the point 1, 0, 4. So at what point do the curves intersect? There we have it, right? So this would be our final answer of 1, 0, 4. All right, the last problem, the last thing that I want to talk about is finding an angle of intersection, right? So basically what we did is that we saw we have these two interesting curves in space, right? And they intersect at this point. And the question is, well, what is that angle that they intersect at? And so the idea here is what we're going to do is find the direction, right? This direction vector at this point. So let's say this here is our direction vector for each one of these. And we remember that we know that to find an angle between vectors, right, we can use the whole dot product back from 12.3. And so if we can find the direction vector, aka, remember, derivative. So if we use a derivative, we can get those nice tangent vectors, and then we can figure out the angle between those tangent vectors. And so that's what we're going to do here. So let's go ahead and spend some time. We're going to take the derivative of our first function here with respect to t. And so with that, what we would have 1, -1, and 2t. And so we have some like interesting direction vectors. Of course, we're interested at that intersection, right? So we figured out that they intersect when t is equal to 1. So I'm going to go ahead and plug in everywhere I see a t, I'm going to plug in a 1. So that is 1, -1, 2. And likewise, right, we need to take the derivative of our second curve. This has s's, so we're going to take an s derivative here. And so when we do that, and again, I'm looking kind of up here at my second curve and taking the derivative with respect to s, I'm going to have -1, 1, and 2s. And at that intersection, remember, s is equal to 2. So I'm going to go ahead and plug in everywhere I see an s, a 2. Because again, kind of you have tangent vectors kind of all along this curve, right? You have a tangent vector over here, you have a tangent vector up here, right? We really want the tangent vector at this specific intersection. And so that's why we need to take the derivative and plug in that special time. In this case, s equals 2. Oops, I forgot to plug in 2 for s. Let's do that. 2 times 2 is going to be 4. So now I have these two vectors, and in order to figure out that angle of intersection, we're just going to figure out the angle between these two tangent vectors. And so let's go ahead and do that. Well, remember, in order to figure out the angle between two vectors, we had back from 12.3 that the dot product can be used, right? We have this formula from 12.3 that says a dot b is equal to the magnitude of a, the magnitude of b, times the cosine of the angle between them. And so we're interested in solving for that angle between these things. And so let's go ahead and evaluate out the dot product. So let's see, 1 times -1 will be -1, -1 times 1 will be -1, and 2 times 4 is going to be 8. The magnitude of the first one, well, that's going to be, let's see, 1, 1, and 4. Again, I'm looking right here and taking the magnitude of that. The magnitude of the second over here, so it's going to be 1, 1, and 16. And again, I'm squaring each one of these, adding them up, and putting that into a square root. That's our formula for a magnitude. And so we're going to have 6 is equal to √6 times √18. And so in order to solve for theta, let's go ahead and divide here. And by the way, there is some simplification that we can do here. So 6 times 18 is going to be 108, right? So √108. And if you spend some time simplifying that, that's the same thing as 36 times 3. So the square root of 36 actually has a very nice square root, mainly 6. And so this is just kind of on the side here. Oh, sorry, let me divide by this here. Cheat using technology a little bit. And so again, this is the square root of 3 times the square root of 36. And the square root of 36 is just 6. So actually these very nicely cancel. And we just have this 1 over √3. So our angle is going to be arc cosine, or cosine inverse of 1 divided by root 3. And that right there would be our final answer. So again, it'd be nice to kind of bottle this. And so I have a theorem for us, right? The angle of intersection between two parametrized curves is given by the angle of intersection, or the angle between the direction vectors when the curves intersect. So those direction vectors, remember, you get from the derivative. So you take the derivative of each one of these. And again, notice that very special when the curves intersect. So we need to know when they intersect, mainly at t equals 1 and s equals 2 in our particular situation, but you would need to solve for this, right? And then that you would plug in. That will give you the vectors. And of course, we know how to find the angle between vectors, right? So think back to 12.3 for finding the angle between vectors. All right, that should do it for our pre-class video. Let me know if you have any questions in Piazza. Otherwise, I will see you guys in class. Take care.